Hello and welcome to this lecture, lecture number 3. So this is the lecture for today. The main topic of discussion is capacitance. And last week, you remember, we had a lecture that was recorded on electric potential and potential energy. So we were able to discuss the difference between electric potential difference, and the potential energy, and the formulas associated with each of those quantities. So today is still on the continuation on electric fields, but now we are discussing capacitors and capacitance. So the content for today, we have about 10 items that we will discuss. First, we'll just begin with some questions, some warm-up questions. Then we look at some basics of a capacitor, what it is, how it stores energy, and then we look at what we call the capacitance, and then we look at a specific type of a capacitor, which is known as the parallel plate capacitor. Then we'll also look at the arrangement of capacitors, where we will begin with capacitors in parallel. We look at the equations related to capacitors in parallel. Then you do the same for capacitors in series. And then finally, I'll give you a few examples, and then an exercise will follow soon after. So I hope you enjoy this lecture. So first thing, let's just have this question. Is on the topic that we had discussed already, but we need to know how to go about it. So we have a question here. A pendulum bob of mass 80 milligrams carrying a charge of 2 times 10 power 8 coulombs is at rest in a horizontal uniform electric field of 2 times 10 power 4 volts per meter. Find the tension in the thread of the pendulum and the angle it makes with the vertical. So this question, it combines two things. It combines the electric field part, and it also combines the mechanical bit, because now we're dealing with tension in the string. So like I said last week, the first thing to do is usually to sketch, so that you get an idea of what the question looks like. So the diagram on the left is just a diagram of the pendulum. You have a small mass that is attached using a string. So obviously you expect that you have a tension in the string, and because the mass has a mass, the bob has a mass, then the weight of the mass must also be included. So we have two main forces. That is the tension that you can see T here, and we have the weight, which is mg. All the others are components. For example, QE is electric force. Remember last 2 lectures ago, we defined electric field intensity as force per unit charge. So if you make force the subject from that formula, you get force is equals to charge times electric field intensity. So this is the force that is pulling the bob away from its rest position. So there's an electric force that is pulling the mass towards the right. Now, the tension, because it is diagonal, then it must have two components. It must have a horizontal component, which is T sine theta, okay? And it must have a vertical component, which is T cos theta. So once you have put all the forces involved in your system, then the next thing to do is to recognize that the the bulb is in equilibrium. So if that is the case, all the forces balance in all directions. For example, horizontally, you will say that T sine theta will be equal to QE. That gives you equation number 1. Then equation number 2 will be T cos theta is equals to mg. So based on those two equations, you will be able to calculate if you need theta. Yeah, I think the question requires you to get theta. You will need to get theta and you calculate the tension. There are two equations and therefore you should be able to solve two unknowns. That is theta and tension. I put this this blue color for to show that they are components of the tension force. Tension is the main force, but it has two components. Weight is the main force. It has no component because it is vertical. Then you have electric force, which is horizontal. It has no component. So you make sure you sketch it correctly. Then you apply now the equilibrium concept. You equate forces that are equal, and then you get the unknowns. So you have two unknowns, then you require two equations. So you will do that, and you make sure you get the answers as indicated down here. You will have to get theta as equal to 27 degrees and tension as equal to 8.81 times 10 to the 184. Please do this, and if you get it correctly, that means you have understood what we are talking about. If you are not able to do to get these answers, please consult your friend just to see maybe you made a mistake somewhere, and maybe you'll get help. So let's go into the bit of introduction. I think this one is a question. Yeah, this is a question. A tiny charged droplet carries one surplus electron, which has a charge of 1.6 times 10 to the negative 19 coulombs. You're told if this droplet is balanced between two parallel plates in a field of 10 power 5 Newton per coulombs. Find the mass of the droplet, and then you have the answer there. So again, you will begin by sketching to try to interpret the question. Then from the sketch, you can now find what is required. That is the mass of the droplet. Again, you will try this and make sure you get the answer as indicated. If you don't, you can consult. So this one was supposed to be part of the introduction, not capacitor yet. So now we begin with the capacitor. So I'm sure this word capacitor is not new. We have heard about it. Maybe some of us have seen what a capacitor is. I think in my slide I should have put a picture of a capacitor, but I think I forgot. So basically a capacitor is a device that stores charge. That is a simple definition of a capacitor. A capacitor is a device that stores charge, electric charge. There are different types of capacitors. We have those ones that are spherical. We have those ones that are cylindrical. We have those ones that are called parallel plates capacitors. And this is the common type. So in our discussion, we will concentrate on the parallel plate capacitors. We will not look at the spherical one, the cylindrical, and all that. But the concept is the same, that a capacitor stores charge and it must have two plates. Okay, one plate is positively charged, the other one becomes negatively charged, and then the amount of charge stored there can now be quantified, can be measured, which we shall discuss later. So this diagram you're seeing here is what we are talking about. One side you have a metal plate or a conducting plate on one side. On the opposite side, you also have another conducting plate or a metal. In between the two metals, you have a material that is an insulator, which is referred to as a dielectric. The material between two parallel plates is referred to as the dielectric. So the three parts form what we call a parallel plate capacitor. The metal rods are connected by some connecting wires, which if you want to connect it to the circuit, then those two terminals will help you do that. So the symbol of a capacitor is what you can see on the diagram B here. You have two parallel lines, and then with the horizontal line to show the terminals, and then C to show that it is a capacitor. So please take note of that symbol of a capacitor as we continue. So in a neutral state, the amount of charges in each plate is always the same. That is to say, in one plate, if you have 10 positive charges, then you have 10 negative charges. So it's basically neutral. The same applies to the other plate. Remember, we have said that a capacitor is composed of two plates with a dielectric in between. The dielectric, let me emphasize a bit, the dielectric, that is the material between the plates, can be made of any type of material. It can be air, okay? It can be paper, it can be ceramic, or any other material. So if it is air, which in most cases we shall assume that it is air, then when we get to the part of using the permittivity, you remember we discussed permittivity, then if it is air, we will use what we call the permittivity of free space. That is the epsilon naught. So in this slide, what I'm trying to show is that when the capacitor is not charged, when it has not stored any charge, then the two plates have neutral state of charges. That means the number of positives equals the number of negatives. All right. So when you connect a source of voltage across the ends of the terminals, when you connect a source of voltage across the ends of the terminals, what you are doing is called, you are charging the capacitor. You are charging the capacitor. So this is what happens. When you put the source of voltage, like we can see here, the positive terminal will attract the negative charges from one plate. Okay? We emphasize that it is negative charges that will move. So the negative charges will move from one plate, move externally through the circuit, and will go to the other plate. So essentially what we are saying is that when electrons leave one plate, the number of positive charges will be excess. For example, if you remove one electron from this plate, the number of positives increase by 1. If you remove 2, the number of positives increase by 2. On the other side, if you add 1 electron, the number of electrons increase by 1. If you put 2, the number of electrons increase by 2. So the flow of the electrons in external circuit forms what we call a charging current. It's called a charging current. So the charging current will continue to flow until the positive charges, you have maximum positive charges on one plate and maximum negative charges on the other plate. When that happens, there will be what we call a potential difference. One plate will be at a potential different from the negative plate. So the difference in potential of the two plates is called the potential difference. That potential difference equals the source of voltage. Okay, so when the potential difference becomes equal to the source of voltage, you will have no more electrons flowing in the external circuit. And at that stage, we say that the capacitor is fully charged. The capacitor is fully charged. So the capacitor will be fully charged when the potential between the plates equals the potential of the source. All right, I hope that is very clear. So the point that you need to remember is that when electrons flow from one plate to the other, a potential difference is created between the plates. When that potential difference becomes equal to the external voltage that is applied, you will have no more electrons flowing. At that point, the capacitor will be fully charged. And once it is fully charged, you can remove it and use it in a different circuit so that it becomes a source of current in itself. So, let me just, okay. So let's continue. In the next slide, what I'm trying to show is that the plates have now attained maximum charges. Like you see, the left plate, you do not have negative charges, you only have positive, and then the right plate, you only have the negative. So at this stage, the capacitor becomes fully charged, and the potential difference between the plates equals to the potential difference by the voltage. So that's what we're saying. When capacitors are first connected to the circuit, electrons are transferred from the left plate through the battery to the right plate, leaving the left plate positively charged and right plate negatively charged. The flow of electrons ceases or stops when the voltage across the capacitor equals that of the battery. We have discussed that. So, like I said, once the capacitor is fully charged, you can remove it and use it externally in another circuit, or uh, it can still remain there, but the charge can be used for other purpose. Okay. The idea behind charging a capacitor is so that the charge that has been stored can be used in a different, it can be used for another purpose within the circuit or externally. So a capacitor retains charge after the source of voltage is withdrawn. A capacitor stores energy in the form of electric field that is established by the opposite charges on the two plates. Okay. So in the definition of a capacitor, we can say that a capacitor is a device that stores charge or energy in form of electric fields. We have other devices that store energy in other forms like magnetic field, but specifically for a capacitor, it stores energy in form of electric field. So a capacitor obeys Coulomb's law. Remember, we say that Coulomb's law is defining the force that exists between charges. So now that we have accumulation of charges on one plate and accumulation of negative charges on the other plate, then you can actually get the Coulomb's law, the force between these two charges, provided you know the quantity of the charge, you know the distance between the plates, and so on. So what is capacitance? Now, you have different capacitors. You can have a small capacitor that stores maybe just a little charges. You have another capacitor that stores maybe a little bit more. You have another capacitor that stores even much more charges. So the quantity that is used to measure how much charge a capacitor can store is called capacitance. Okay, so you can say that this capacitor has a capacitance of 10 microfarads. Another capacitor you can say stores maybe 20 microfarads. So it simply means that different capacitors have different rooms, or you can call it, let's call it rooms, to store different charges. So a small room will store a small charge. So we call it small capacitance. Another capacitor that stores a lot of charges, maybe it has a bigger room, we said the capacitance is big. So the capacitance of a capacitor is defined as the ratio of the magnitude of the charge on either conductor to the potential difference between the plates. That is, you get the mathematical bit of it. Capacitance is also described as a measure of the capacitor's ability to store charge. The capacitance of capacitor is the amount of charge the capacitor can store per unit potential difference. So you can see the first three bullets that we have here, we are only trying to understand how you can describe capacitance. We can talk about it as the ratio of charge to the potential difference. I think that is in bullet 1 and 3. You can install it as the measure of capacitor ability to store charge and so on. But then, if we pick from bullet 1 and 3, capacitance can be written mathematically as charge per unit coulomb. This is very important. Some sections you will find it written as Q is equals to CV. Okay, and the SI unit of capacitance is farad. Now, 1 farad is a very large value. So you will find that the units that is used most of the time when you are giving the quantity for capacitance is in smaller units like micro, pico. So micro simply means it is 10 power negative 6. 1 microfarad is 10 power negative 6 farads. Then picofarad simply refers to 10 power negative 12 farads. And if it is 10 power negative 9, that becomes nanofarad. So capacitance is always a positive quantity and it is constant. That means for one capacitor, the capacitance remains the same. Whether you store more charge or less charge, the capacitance remains the same. The value for the capacitance does not change. It changes from capacitor to capacitor, but it does not change within one capacitor. So the capacitance C of a parallel plate capacitor increases linearly with the area of the plates for a given potential difference. So here we have already said that a capacitor is a device that contains two plates with a dielectric. So the capacitance, if you want to increase the capacity of the capacitor, you can make the plate very big. That means you increase the area. Okay, and the other quantity, the other property or factor that determines the capacitance is the distance between the plates. That is d, small d here. So the smaller the distance, if the plates are too close, it means the capacitance is very big. So if you want to increase the capacity of your capacitor, you make the distance very small and you make the area very big. And this is what is shown in equation number 3. That capacitance is equals to the permittivity of free space times the cross-sectional area of the plates divided by the distance between the plates. We are using permittivity of free space because we are imagining that the plates, there is air between the plates. If you have a different material, then this one would be the permittivity of that particular material. The permittivity of that material. So how to arrive at number 3, equation number 3, you can see it is shown here in equation number 2. We have the main formula, capacitor is equals to charge per unit voltage. Voltage is equals to electric field intensity times distance. You can remember this, we discussed last week. And then if you now put what is this? The electric field intensity, we also defined it as Q over epsilon naught times R squared. I think you need to go back to that equation and see how the quantity A comes about. The quantity A comes about because the electric field intensity is defined with R squared. So we are assuming if you are dealing with a square plate, then the area is the length squared. That's why we have an introduction of area. So please go back to that lecture, try to see how the electric field intensity was defined, and try to connect uh, try to connect that with the cross-sectional area. And so equation number 3 is very important. It shows that capacitance depends on the geometrical area of the plates and the distance between the plates. So this is just an emphasis again of equation number 3, that capacitance depends on the cross-sectional area and the distance between the plates. Again, let me emphasize that because it is only epsilon naught, the assumption is that what is existing between the plates is air or vacuum. If there's a different material, then we have to include the permittivity of the material, or we use the relative permittivity. All right, so this brings us to our next part, which is connecting capacitors in different ways. So the first way to connect capacitors is to put them in parallel. We all know from our knowledge of DC electricity that when components are connected in parallel, then voltage across each component becomes the same. Voltage across components in parallel is always the same. That is to say that the voltage V1 in the diagram here is equal to the voltage V2, is equal to the voltage V3, is equal to voltage Vn, which is equal to the voltage of the source, that is V. So it doesn't matter how many components you have. If there are only two, then you say V1 is equals to V2 is equals to V. If there are three, V1 is equals to V2 is equals to V3, which is equals to V, and so on and so forth. So here, the concept is that for a parallel components, you have voltage equals the same. So V is the terminal voltage. Let's see what happens next. So then, the total charge when components are connected in parallel is not the same in each branch. Okay, so you have the total charge being distributed in each arm. Let me go back to my previous slide. So you have the total charge in the circuit being distributed in this arm, into this arm, into this arm, into this arm. In other words, the charge behaves like current when you are dealing with resistors. If it is in parallel, you have current distributing in all the arms. So the total charge will be equal to Q1 plus Q2 plus Q3 up to whatever number that you have. So the capacitors can be replaced with one capacitor with a single equivalent capacitance CEQ. So that's what we need to get. So we have already seen two concepts. One, potential difference is the same across. The total charge is the sum of individual charges. So equation number 6, we can substitute Q using the formula Q is equal to CV so that we can include the capacitance in that equation number 6. So if we replace equation number 6 with Q is equal to CV, we will get the total charge goes with total main voltage is equals to, for Q1, we have the capacitance C1 times V. Remember here, we are using V throughout because the voltage is the same. So you do the same up to the last capacitor. And of course, since V is constant in all the terms, you can simply remove, or you can factorize V and then it will cancel out. So finally, you will have that when capacitors are connected in parallel, the total capacitance is equal to C1 plus C2 plus C3 up to the last. So please take note, in parallel, capacitors are added the normal way, just a normal addition, C1 plus C2 plus C3 up to the last one, right? And the process which we use to derive is explained. So then let's look at the next connection. When you are dealing with the capacitors in series, then you have one terminal connected to the terminal of the opposite sign, then the next terminal connected to the terminal of the opposite sign, and so on and so forth. So again, when you connect an external voltage, you'll have charging current flowing and charges accumulating on the plates, right? So that the charge that is stored in the charge that flows in C1, C2, C3 up to Cn is essentially the same because they are in series. Like I said, charge behaves like current. And in other words, the definition of current is the rate of flow of charges. So charge and current behave the same way. So in this case, the charge is the same. The only difference is that total voltage V will be a summation of V1, V2, V3 up to the last one. So we say here down here, the potential difference across capacitors are, for example, V1 will be charge over capacitance. Here we don't have Q1, Q2, Q3 because the charge is the same. So for V1, we shall have Q over C1. For V2, we'll have Q over C2. For V3, we shall have Q over C3. For the last one, Vn, we have Q over Cn respectively. So each capacitor, the voltage across each capacitor is obtained using the main formula U is equals to CV. So let's proceed. So from the figure, we see that the potential difference is simply the sum of all individual potential differences because they are in series. So we say that the main voltage V equals V1 V plus V2 plus V3 up to the last one. Then we need to replace these capacitors with a single capacitor. In other words, we are looking for an equivalent capacitor that will behave the same way as all this. So to do this, we will use the total main capacitor, the main charge Q and the total voltage V. So we'll say the total capacitance will be Q over V, where V is now the main voltage and Q is the constant charge. So if we do that, if we substitute, let me say which equation, if we substitute in equation 9, we substitute in equation 9 so that we have, this is like V, this is V1, this is V2, this is V3 up to the last one. We do that and then we factorize Q and then we cancel. We'll find that Q on the left and Q on the right will cancel out. So essentially what you remain with is that 1 over the total capacitance equals 1 over the first capacitance plus 1 over the second capacitance plus 1 over the third capacitance up to the last one. So in series, the total capacitance is the reciprocal of each capacitance, and the main capacitance is equal to, it will be 1 over the main capacitance will be equal to the sum of reciprocals of each individual capacitances. So I hope you don't forget this, because the way you treat um, capacitors and the way you treat resistors, which I'm sure you already have the knowledge, is a bit different. I mean, in series for capacitors is the reciprocal. In parallel for capacitors is direct summation. So please take note of this difference, because I'm sure you're meeting this for the first time. So let's look at a simple example here. You have a question which says a parallel plate capacitor is to be designed with a voltage rating 1 kilovolts using a material of dielectric constant 3 and dielectric strength 10 times 10 power 7 volts per meter. What minimum area of the plate is required to have a capacitance of 50 picofarads? Good question. The first thing you do is to write the equation that we have discussed, the equation connecting the cross-section area and the distance between the plates. So equation number 12 is used only when the medium between the plates is air. Okay? But this question, if you read it keenly, we have been told that there's a material. There is a material between the plates, and therefore we have been given the dielectric constant or the relative permittivity. So epsilon naught times epsilon r will give you the permittivity of the material. All right? We have to use epsilon r because that is what we have been given in the question. So equation number 13 is important. And from here, we simply make cross-sectional area the subject, and we have the capacitance C. Do we? Yes, we have. Capacitance C is 50 picofarads. The distance between the plates, do we know? Okay, it can be calculated. Epsilon naught is a constant, which we already know it, and permittivity, the relative permittivity is given as 3. So this D is what is not given directly, but we know that the distance between the plates is equal to voltage over electric field strength. In other words, we define this one differently, that electric field strength is voltage over distance. So we use this expression to calculate your distance D. So once you have your D, you come to question number 14, you substitute and you get your area of the plates. I don't think this was complicated. You just needed to remember the formula and remember to use the relative permittivity of the material. Example number 2. The total capacitance of two capacitors is 4 when connected in series and 18 when connected in parallel. Find the capacitance of each capacitor. This is a good question. So how to go about it? First, you put your variables. You say let C1 and C2 be the unknown capacitances of the two capacitors. So that's what you need to calculate. So in series, we know that the total capacitance is the reciprocal. So you say 1 over C1 plus 1 over C2 will be equal to 1 over 4. Remember, the units will be microfarads. So again, in parallel, it is simply the sum, which is C1 plus C2 gives you 18. So this one is more like straightforward. If you did simultaneous equation in form 2, this should be a glass of water for you. This is basically simultaneous equation, and you solve it the normal way, and you'll get your two answers, C1 as 12 microfarads and C2 as 6 microfarads. So again, I will encourage you to try this and confirm your answers. Example number 3, is a little bit advanced. You are told that two capacitors A and B are connected in series across a 200 volts DC supply. The potential difference across A is 120 volts. This potential difference is increased to 140 when a 3 microfarad capacitor is connected in parallel with B. Calculate the capacitances of A and B. Good question. So, first thing, you do a sketch of how you understand the question. You have been told that A and B are connected in series across a 200 volts DC, and then capacitor A takes 120 volts. Of course, capacitor B will take the rest, which is 200 minus 120. That's 80. That is the diagram on the left. Then you're told the next condition is this, that the potential difference is increased to 140 when a 3 microfarad capacitor is connected in parallel. So you do a sketch again. You put a 3 microfarad capacitor in parallel to B, and the voltage across A becomes now 140, and of course the source is not changed. So you need to calculate the capacitances of capacitor A and B, which we are calling here C1 and C2. So you start working. You say from figure 1, charge is constant because it is in series. So charge passing through A or charge stored in A equals to charge stored in B. For a simple reason, they are in series. And what is the formula for charge? Capacitor times voltage, CV. So you'll say C1 times 120, that is the charge across A. Then you have C2 times 80, that is charge stored in B. So from this, you simplify it, and you'll end up with C1 is 2 over 3 C2. So that becomes your equation number 16, and you keep it aside. Then you proceed. In the figure number 2, the capacitance in parallel section is C2 plus 3. Let me go back and see that. You see this figure B here, these two capacitors are in parallel. And if they're in parallel, the total capacitance here is simply 3 plus C2, where C2 is the capacitance of B. Okay? C2 plus 3. The two parts can be treated as series connection. The two parts can be treated as series connection with equal charges. So this becomes a single capacitor in series with capacitor C1. So once you have created that idea of series, then you say the total charge becomes the same. So C1 times 140 is charge stored in A. Then charge stored in the parallel connection, you have total capacitance here, which is C2 plus 3 times the voltage, which is 60. So you simplify this. You open the bracket and you simplify. You make it simple so that it becomes 7C1 minus 3C2 equals 9. So again, we all went through form 2. We were taught how to do simultaneous equation. Equation 16 and 17 are simultaneous, and so you solve them and you get your C1 as 3.6 and C2 as 5.4. Try this and make sure you confirm those answers. So the important thing in this question is, how do you interpret, or how do you bring in the idea of parallel, and how do you get the total capacitance, and how do you treat with the series capacitance? So please, that's a good question. So this one is an exercise which I want you to try. You read it, interpret it, and please let's share our answers in our next lecture. I thought this one is a good question for you to try, or maybe to test yourself. and see how well you can do. And I think that should mark the end of our lecture. It's been a small lecture, but I've explained everything. Go through the PDF that I uploaded in the LMS system, and if there are sections that you don't understand, you go to the video. You can pause like I told you last time, and watch it several times until you get. Again, I encourage you to look at as many questions as you can, um, and share your answers with your friends or with me, provided you make sure we move along together. So I think that should be the end of the lecture. Let's hope to meet again in our next lecture next week. So thank you very much and have a nice day.